A warm greetings to you all. Myself Vishal Babu Guggari, research scholar in Department of Mining Engineering, Indian Institute of Technology, Dhanbad. My research topic is stability analysis of a crown pillar under the zone of relaxation around sublevel open stopes using numerical modeling. So before starting, let's understand what is mining. Mining is extraction of minerals from earth by safely and economically. So in mining, we have a two major classification. One is underground mining, and another one is open cast mining. And again, in underground mining, we have a two major classification. One is underground coal mining, and another one is underground metal mining. So my research comes under underground metal mining. So again, in underground metal mining, we have a different extraction methods. So the extraction method depends on the condition of the ore body and as well as the condition of the adjacent strata. So in which sublevel stoping is also one of the extraction method, in which the massive and tabular ore deposits with the steep dips are being used to excavate by using this method. So in which large diameter blast hole is also a type of sublevel stoping where we use a large diameter blast hole for blasting the ore body. So in this figure you can see this is an ore body. This is a ore body which has a very steep dip from the surface, and in the during the stoping procedure, the first thing is we need to do some development works. So in which we make two levels. One is at the top, we call, let us consider it as a top level, and another one is at the bottom, so we call this as a bottom level. So in between this top level and bottom level, we need to make another level which we call it as a sub level. So that's why the name called sub level stoping. So here, after making the initial development work by making the levels, so we start drilling a large diameter blast holes from top level to sub level at particular pattern with a particular pattern, and then from sub level to bottom level. So after drilling, we'll fill these holes with an explosives and then start blasting at a particular phase of 15 meters each in this direction. The blasted material will fall into the bottom level, and this blasted material will be withdrawn from this haulage drive, which is driven parallel to this bottom level. And the series of cross cuts at regular intervals will be made in between the bottom level to this drivage level. And this broken ore or a broken material will be withdrawn through these cross cuts, and it will be transported through this haulage drives, and then it will be hoisted to the surface. The space or the void space which is left after mining or excavation, that we call it as a stope. So, in order to support or in order to stabilize this stope, we will leave the horizontal pillars at the top of each stope, that we call it as a crown pillar. So, the motivation for this research comes from, let us consider a cross section of the same stope which I have explained earlier. Let us consider this stope is empty and it is completely extracted, and after extraction the stresses will be redistributed in the form of an arch. So during this redistribution of the stresses, so the existing joints will be enlarged and it will be widened. In this process, the stresses will get released. So this zone becomes a stress relaxation zone. So these stress relaxation zones develops a tensile stresses, and this tensile zone or a stress relaxation zone may fall into this white space at any time. So hence we need to know the behavior of this relaxation zone, and we need to design a crown pillar in such a way that this relaxation zone gets minimized or stabilized, and as well as the crown pillar should also be stable. So there are two major objectives of this research. One is to design a crown pillar which is left at the top of this top of each stope by considering a different parameters such as rock mass conditions, excavation width, and as well as depth. And one more major objective of this research is to know the behavior of this crown pillar, to know the behavior of this crown pillar around this relaxation zones. So in order to achieve the objectives, so we have selected one deep mine in India, which has a ore body at a depth dipping an average of 60 to 70 degrees from the surface in the direction of northwest to southeast. So the rock which is above this ore body, which we call it as a hanging wall, and the rock which is below the ore body, which we call it as a footwall. And the payable width of the ore bodies is varying from 2 meters to 20 meters. And the above, from this level of around 548 meters, the above stopes are excavated by using a shrinkage stoping, and which is used earlier, and it is very old method. And the site which is under investigation is in between 548 meters to 792 meters. And around this, in this investigation area, a sub-level stoping method has been adopted. So rock mass properties are also very important for a numerical modeling, because these are the basic input parameters which we need to give for the simulation process. So hence, in order to estimate the rock mass properties, we have conducted a series of studies in the field and as well as the laboratory. So in which geotechnical study was conducted in the field in order to know the conditions of the joints, joint spacing, and orientation conditions, which deals with the geological discontinuities, which directly affects the strength parameters. So the rock samples were collected below 548 meter, and 50 core samples were tested for a uniaxial triaxial compression testing, and another 35 core samples were tested for a biaxial tensile strength. So from the laboratory study, we got to know that the ore body has a varying strength parameters, large variations in the strength parameters such as UCS, which is varying from 67 to 202 MPa, and Young's modulus, which is varying from 38 to 70 GPa, and the geological strength index, which includes the geological disturbances. This index gives a particular value for the rock masses. The lower value shows that which has a more number of geological discontinuities, and the value which has a higher GSI, it has a few geological disturbances, and this GSI is also varying from 45 to 75, and again friction angle and the cohesion is also varying accordingly. So by this, so we have we have taken a number of variations in each parameter, such as a crown pillar, we have taken four variations, and in GSI we have taken four variations. Modulus, Young's modulus or elastic modulus, we have taken three variations, and UCS we have taken four variations. So in the through these variations, so we have done a parametric analysis in order to know the behavior of the crown pillar and as well as the stability of the crown pillar under the zone of relaxation. So now coming to the description of the models, a finite element method is used for the numerical modeling, and the software which is used is ANSYS for the simulation, for the numerical simulations, in which 240 finite element models were developed according to the combinations which we have already considered for the parametric study, in which 192 models are excavation models and 42 models are in situ models. The actual dip and the actual dimensions of the ore body has been considered for a development of numerical modeling, and again The mesh has been generated, a fine mesh has been generated near the area of interest, which you can see in the figure, and the coarser mesh has been generated away from the area of interest at a growth rate of 1.05 in order to reduce the computational time. So the number of elements is also very, very important because it directly proportionate to the accuracy of the results. So in order to find the optimum number of elements, so we have conducted a mesh sensitive analysis. So in which in each iteration we have increased the number of elements, and uh, mm, we have seen the effect of this element count on the results. So and it has been plotted in this figure along with the element count and the stress values. So in which you can see here we have obtained an optimal solution or optimal element count where the effect of element count is not affecting the results, after this optimized element count. So this optimized element counts is around 1,59,328 quadratic triangular elements are used for each models. And even the boundary conditions are also applied, where the in situ stresses were measured in the field, and those in situ stresses are applied on the models, in which the vertical stress of 7.67 MPa is applied on the top of the each model, and the horizontal stresses of horizontal varying uniform varying load has been applied on each side of the stopes, and even the roller constraint is applied at the bottom of the stopes. The few assumption has been made during the simulations, in which the plane strain condition has been assumed because the it is a 2D problem, in which the plane strain condition assumes that the deformation occurs only in a two dimensions and there is no deformation in the third dimensions. And even the property does not change with depth. If you consider a single model, it has a cumulative single property to the model, but it does not change along with the depth. And the particular joint or a bending plane is not analyzed explicitly, and these joints or bending plane or the geological distribution has been considered in the GSI and RMR values. And again, the static load has been applied. There is no dynamic load which is applied on each models. So model calibration is important because we need to calibrate. Because the model it has been generated uh, in the computer. So hence the result should be calibrated with the in situ measurements. So that for that purpose, so we have measured stress values at a depth of 731 meters, which has shown in this table. The sigma x and sigma y has been measured at a depth of 731 meters with the help of load cells or stress load cells, and as well as the stress cells too. And these values has been compared with the model measurements, and the exact location we have measured in the model, and the values you can see, it is compared with the in situ measurements and the model measurements, where the values are very comparable and reliable, because the difference between these two is very, very minimal. The results of the FE models, finite element models, the results are presented in terms of stresses, deformation, and as well as the yield zones. So the principal stresses is very important in order to find out the safety factor of any structure of any underground structure. The safety factor, if it is less than one, indicates that the underground structure is going to fail, or if it is greater than one, the structure or the underground structure is safer. As you can see in this figure, the relaxation zone which has generated or developed due to the excavation of the stopes. And this figure shows the major principal stress distribution, and this figure shows the minor principal stress distributions. Now coming to the parametric analysis, that is principal stresses based on depth. This figure shows the major principal stress distribution, and this figure shows the minor stress distribution. So in which depth has been varied, and the each depth crown pillar has been analyzed for the principal stress distribution, and this figure shows a 0609 meters, and this figure shows a 670 meters depth, and this figure shows 731 meters depth. So in which in general what happens, as you go deeper and deeper, the stresses, the in situ and as well as the induced stresses increases. But in this condition you can observe that at the center of the crown pillar the stress is reducing, as you can observe from the figure. Even for the major principal stresses and even for the minor principal stresses is also decreasing as you go deeper and deeper. The reason behind this is again this relaxation zone. Hence it is very important for this study to know the behavior of these crown pillars under this relaxation zone. See, as you can see, the stresses should increase, but in this condition the stresses are decreasing as you increase the depth of the working. It is just because of the stress distribution, which is the stress has been distributed in the form of an arch, where you can see as you go deeper and deeper this arch shape is getting minimized. So hence the each depth, the results are in the sense the stresses are reducing as you increase the depth of the working. As you can see, as you go deeper and deeper, in case of minor principal stresses, the tensile zone has been generated. As you can see, a blue region in this figure shows a tensile stresses, in which if these tensile stresses exceeds the tensile strength of the rock mass, then obviously this structure is going to fail. So hence it is very important to know the principal stress distribution, which in terms identifies or indicates the failure zones of the rock mass or underground structure. Now coming to the pillar thickness. So this figure shows a 5 meter pillar thickness, and this one shows a 6 meter pillar thickness. This one shows a 7. This one shows an 18. Sorry, 8 meter prone pillar thickness. So here also you can observe that as you increase the pillar thickness, again the stresses at the center of the crown pillar, the stress concentration at the center of the crown pillar is increasing as you increase the pillar thickness. And again, in case of minor principal stress distribution, also the same phenomenon you can observe, where the stress concentration is increasing as the pillar thickness increases. Because again, the reason for this is again the same relaxation zone. So as you increase the pillar thickness, what happens is it can take more load from the adjacent strata. So by extent of the thus reducing the extent of the relaxation zone. So as a result, it is taking a huge load from the existing strata. Thus the thickness, thus the crown pillar is experiencing a huge stress concentration at the center of the crown pillar as you increase the pillar thickness, because the load bearing capacity increases as you increase the pillar thickness. So coming to GSI, again, as I said, if the rock mass has a lower value of GSI, it indicates that it has a more geological discontinuities, and again it reduces. If you have a more geological discontinuities in the rock mass, it reduces the strength. So again, the rock mass which has a higher value of GSI, it indicates that it has a less or a few geological disturbances. Again it indicates it indicates that the strength of the rock mass is much higher because the discontinuities is very less. So again, as I can say, the GSI value, which the value of a rock mass which is higher, has a more bearing capacity because the strength increases because due to a lesser or a few geological disturbances. So here you can see as the GSI value increases, from 45 to 75, 45 to 75, the stress concentration at the center of the crown pillar is reducing by increasing the pillar thickness. By increasing the GSI value. And again, in case of uh, minor principal stress distribution, the same phenomenon you can observe where the stress concentration at the center of the crown pillar is reducing as the GSI of the rock mass is increasing. Now coming to the modulus of elasticity, where here you can observe at the center of the pillar, the stress concentration is reducing as the modulus of elasticity increases. And again, in case of minor principal stress distribution, again you can see the same phenomenon has a stress concentration at the center of the crown pillar is reducing as you increase the elastic modulus. Again, when it comes to UCS indicates the strength of the rock mass, where it indicates the load bearing capacity. As I said, as we have already discussed, in case of a pillar thickness, as you increase the pillar thickness, even the stress bearing capacity increases. Again, in case of UCS, also the same thing happens. As if the higher UCS has a capability of taking a more load from that adjacent strata, and again due to the taking a huge load, so again at the center of the crown pillar, what happens is the stress concentration increases. So as you can see at the center of the crown pillar, the stress distribution or the stress concentration increases as you increase the UCS of the crown pillar. And again, uh, in case of minor principal stresses, the same phenomenon you can observe where the stress is increasing, the stress concentration and as well as the magnitude of the concentration stress is increasing as you increase the UCS. Now coming to the analysis of the vertical deformation, the vertical deformation has been measured at the bottom of the crown pillar from A to A dash, and it has been plotted with a vertical deformation with the width of the whole body. So here at the table, you can see a negative where negative sign indicates the downward movement of the rock mass, where you can see the effect of depth on a vertical deformation. So as you go deeper and deeper, the deformation should increase. So here in this figure, you can see as you go deeper and deeper, the deformation is also increasing. So here you can see from 609 meters to 670 meters. So there is an increase in deformation by 41.25%. As in case of pillar thickness, the vertical deformation is also increasing as you, the vertical deformation is decreasing as you increase the pillar thickness. As in case of GSI, again, we have already discussed about the values of the GSI, where it indicates the presence of geological disturbances and as well as the strength parameter, how it affects the strength parameters. So again, as you increase the GSI of the rock mass or ore body, the deformation reduces. When it comes to modulus of elasticity, again, where you can see there is not much there is a negligible effect on each variations in E. As you can see, and the variation is very similar to each other. So there is a very negligible effect of elastic modulus on vertical deformation. So as you can see in case of UCS, again UCS directly proportionate to the strength parameter of the rock mass. So hence, as you increase the UCS, it increases the load bearing capacity, and it becomes a very robust when we have a higher UCS. So hence, it resists the deformation. So here you can see as you increase the UCS, the vertical deformation is also reducing. Now coming to the analysis of the plastic zones, plastic zone indicates that the uh, plastic zone indicates that the that particular area where there is a high plastic intensity or plastic deformation or plastic zones is there. So it indicates that that particular area has a safety factor which is less than one. Less than one in the sense it is a failure zone. Directly it implies that, or directly it is showing the failure zones of the rock mass or a prone pillar. So as you can see, the effect of D on a yielding zones. So here the extent of the yielding zone has been measured, and it has been plotted or noted on in the table. So as you can see, as you go deeper and deeper, the extent of the yielding zone is increasing. Extent of the yielding zone is increasing as you go deeper and deeper. So as when it comes to a pillar thickness, again, as you increase the pillar thickness, the extent of the yielding zone, the maximum yielding zone is reducing, and even the extent of the yielding zone also, if you observe from the figure, it is reducing. The effect of GSI on the yielding zones, again, as you can see from the figure, the extent and as well as the magnitude of the yield zone is reducing as you increase the GSI. When it comes to modulus of elasticity, again the elastic again sorry again the yield zone is reducing, or the extent of yield zone is reducing. I'm I'm very sorry, I'm a bit confused. So here let me say, the extent and the magnitude of the yielding zone is increasing as you increase the elastic modulus. When it comes to UCS, you can observe that, as we have already discussed, how the UCS affects on the stresses and as well as the deformation. And here, in case of yielding zone, also as you increase the uh, UCS value, the deformation, the plastic deformation or a plastic zone reduces. Now, coming to the conclusions, it is very important to know the major principal stresses which directly indicates or give an idea of a failure zones where the failure zones may occur. So hence it is very important to know the behavior of the major and minor principal stresses in case of stress analysis. So as we have already seen that as you go deeper and deeper, the stresses should increase, but due to the development of the relaxation zone around the stopes, the stresses in the crown pillar is reducing as you go deeper and deeper. And again, the GSIE and UCS has a major significant impact on the vertical deformation and as well as the plastic zone. Those in general or in final, this study suggests that the 6 meter prone pillar is safer up to only depth of 670.56 meter, and above that, that is 7 meter or greater, should be used, or for a greater depth of around 670 meters below. A thin pillar of 5 meter is not recommended at all for any kind of a geomining circumstances due to a severe yielding has been observed at a greater depth. So hence the behavior of thin pillar is not much acceptable. So hence this 5 meter pillar is not suggested or recommended for any kind of any geomining circumstances. Thank you.